Good morning, good afternoon, good evening, whenever you're watching this. You should be watching this during class at least once, but maybe you're watching it another time. So howdy, how are you? Thanks for watching. Um, I'm gone. I'm absent. So here I am. Right? Today we're doing the 2.4 lesson. We're skipping 2.3. Um, this will conclude our chapter 2. So when I get back, we will review chapter 2 that quick. 3 lessons just like that. Another 3 lessons. So scores have been really good on the assignments for 2.1 and 2.2. So I'm really proud of you. I'm really happy about that. And let's hope for the same here with 2.4. And without further ado, let's go ahead and jump in. So still sticking with our quadratic functions, um, let's take a look at what this has to say. The graph shows a quadratic function p, which approximates the yearly profits for a company, and t is time and p is the profits. So if you're looking at this graph and this represents the profits were up here, went down a little bit, and then back up, and now they're going to keep going up. Right? That's how a quadratic function works. It's going to make this U shape. So if the fact that this parabola is opening upwards means that the a value is going to have to be positive because it's opening upward. Okay, so there's that. We can make that assumption. This is not a, I'll write positive. That almost looks like a T. Write an expression in terms of A and B that represents the year when the company made the least profit. So let's think about visually. Where does the least amount of profit occur? It's going to happen at the minimum. Right? It's going to happen here at the bottom of the graph. And what do we call that point again? That is the vertex. So basically what it's asking is essentially, what is the vertex? Now, we're in standard form, and there was an equation in 2.2 that you probably don't remember, and that's perfectly okay. You can find the axis of symmetry. In other words, we can find that t value for the year by doing the following. Negative b over 2a. Okay? So that is the year that the least amount of profit occurred. So don't worry about the numbers, right? We don't have A, we don't have B, we don't have C, but just realize that the axis of symmetry right there at the very bottom is where the year occurs when we don't have as much money. The company made the same yearly profits in 2004 and 2012. Estimate the year in which the company made the least amount of profit. So this is the equation for the year when they made the least amount of profit, but they gave us some more specific numbers here. It's what they're revealing to us is the symmetry. So they're like, hey, the profit was the same in 2004 as it was in 2012. So that means that the vertex in the middle, right, where it's symmetrical, had to occur between 2004 and 2012, which is 2008. The middle. Beautiful. Assume that this model is still valid today. Are the yearly profits currently increasing, decreasing, or constant? Well, they're definitely increasing because our parabola is on its way up now. It's not going to come back down for any reason. If this is 2012, for example, that means as time goes on, it's just going to continue up. And out here is 2021, right? So it's still increasing. Lovely. I know there wasn't any numbers really for that except for 2008, but hopefully you can get the idea, even without numbers, how this graph P can represent the profit increasing over time. Let's look at one with some more concrete numbers. The table shows the heights h in feet of a wrench t seconds after it has been dropped from a building. So the wrench starts on top of the building, right? The height here is all the way up at 400 feet. But when it drops, it's going to very quickly drop in a matter of seconds. So t our time, and it just drops down. Okay. So the height is getting shorter and shorter and shorter. It's reaching the ground as time goes on. 1 second after it drops, it's this 2 seconds after it drops, 3 seconds after it drops, 4 seconds after it drops. Eventually, it takes a little bit of time to drop. Eventually it'll hit the ground. So using a graphing calculator to create a scatter plot of the data as shown on the right, explain why the data appears to fit a quadratic model. So we can do this without plotting it. We can see this U shape. But that's all I need you to see, is that as it's dropping, it's creating this parabolic shape. Now we just need to see that it's not going linearly, right? It's not something like this. It's got this parabolic curve to it. Use the quadratic regression feature to find a model for the data. So that's what we were doing with our lines in the last unit, where we were doing the y1 mx1b and we were finding an equation that would model it. We're going to do the exact same thing except with quadratics. So hopefully this feels rather familiar. So these are just random points. So here's what the equation looks like, and I can kind of zoom in a little bit for you. So it looks very similar, right? Y1, X1, but you can see here I've typed it in vertex form. Before it was slope intercept form. Now we're here in vertex form. So let's go ahead and plug those points in. I'm going to pause so you don't have to watch this part and the video's not super long. So I'm going to look at the graph right here and I'm going to plot those points into my function and I'll be right back. Okay. Okay, I'm back just like that. I took a look at this table and I entered the points, and this is what my parabola looks like. Just so you know, I edited the scale so that way you can really see the parabolic shape. So I made it 400 at the top here, and then I went from like 5 to -5 on the sides. So there's my parabolic shape. You can see each of those points that have been plotted. And you can see over here on the left how it's automatically calculating everything, right? It's got the A value, it's got the K value. Ooh, Desmos is being weird here. We can see that the vertex is at 0, comma 400, so H should just be 0. It did not shift left or right. Um, this is scientific notation, right? I don't know why it doesn't say 0. We might have to stay on the lookout for that, right? So we need to see it visually as well. The vertex is at 0, 400. So with that being said, let's go ahead and write our equation. We've got y equals, the a value is -16, x minus 0. I'm going to go ahead and write the 0 because it didn't vertically shift, and then it moved all the way up to 400. Apparently there's a little bit of an inaccuracy there with Desmos because that number is essentially 0. It's so tiny. This is scientific notation. This is a really tiny number. It's essentially 0. So we're going to call it 0, okay? So stay on the lookout for that. So you can see how our graph and the points match up beautifully. That's all that C was asking us. So beautiful. And then when does the wrench hit the ground? Explain. This is a question that you really need to know the answer to and understand the logic behind it, because this is like a lot of the questions that get asked, like when does this happen or where does this happen? Explain, explain. So we need to understand what we're looking at here. So if this is this red, this does not represent the path of the wrench. This represents the height of the wrench. Okay, so the height of the wrench is 400 feet before we drop it. 1 second after we drop it, it hits, you know, 1,384, then 2 seconds, then 3 seconds, then 4 seconds. So 5 seconds after we drop it, it touches the ground. Explain our answer? Well, the height is 0 at after 5 seconds. So if the height is 0, that means it must have hit the ground. So I'm just writing 5 seconds. The height is 0 because this red graph represents the height, and the second the height says 0, we hit the ground. So I just want you to, we don't need to write some fluffy sentence here, but I just need you to realize, like, how can you use a quadratic function to model a real life situation? But the points can end up in a parabolic shape, and then all of a sudden this parabolic shape represents this, that, or the other, whether it's the height, whether it's profit, whether it's I don't know what, right? And number 4 says use the internet to reference some other examples. Um, if I just quickly type like what what can be modeled by quadratic functions. So I paused that there for half a second to find a good site that had plenty of um, real life examples. We got the value of a car decreasing. We've got the height of a ball. We've got profit here again. We've got um, the amount of time it took to do something. The underpass is like a literal parabolic shape, like the road that you drive on. I like that one a lot, right? A rainbow, sort of like a parabola, right? You could model the path of the rainbow. Um, Selling things here again. So, I mean, think of how many times you've seen something that's a somewhat parabolic shape, right? Whether it's a road, whether it's a bridge, whether it's whatever that is, you could be representing that with a parabolic function, with a quadratic function. So let's define some words as we dive into a few more examples. Average rate of change. This is essentially kind of like slope, except parabolas don't have slope, right? So it's as if you averaged the trajectory all together, right? Kind of like slope, except parabolas don't have slope. So it's like as if you average it all together, right? Like what is the average change throughout? Because it changed quickly here, but as the parabola slows down, it's like if you average those all together, that would be your average rate of change. And then we don't care. Okay. So let's review this real quick. We've got vertex form. We saw intercept form last class as well. We know the vertex. Um, we know the x-intercepts. If you don't recall, right, here's my graph. The x-intercepts are where it crosses the x-axis, and that's what P and Q are, okay? So when you have a graph, this one might be P, and this one might be Q, okay? We know everything about this at this point, right? You plot that, and then this is HK. So let's get into it. Um, let's jump straight into a couple of these word problems. We'll look at these in a minute. Let's dive straight into the more wordier, like real life situation problems. Analyze the differences in the outputs to determine the data as linear, quadratic, or neither. If linear or quadratic, write an equation that fits the data. So we're going to be using Desmos a lot here, okay? So I'm going to go ahead and plug those numbers into the function. I'll pause again so this video isn't too long. Welcome back. So you can see here for number 9 that as I entered those points, they're clearly making a parabolic shape, and my function that I had already typed in here auto-calculated all the numbers, and you can see what we're looking at here. So we'll go ahead and round to the tenths. Let's just go ahead and make a note. Let's just go ahead and make a note on our notes here that we'll go ahead and just round everything to the 10th. So with that being said, this equation would be, I've got the numbers here in front of me. Um, well, you know what? Let's do hundredths. I'm gonna change my mind. If that's okay. I'm gonna change my mind. So let's do negative 15.93 parenthesis x minus h plus k. Well, so those are the numbers straight from Desmos. Maybe while you're writing that down, I'm going to start typing the numbers from the other graph just to expedite things here. So, but before I get rid of it, let's go back. So I plotted the points. I already had this typed in. So as I was plotting the points, it was calculating the numbers. And we got this lovely parabolic shape with A, H, and K. Those are the A, H, and Ks that I just used in my equation. Okay. So let me go ahead and pause again and get these numbers typed in. All right, so kind of funny here. So I went ahead and plotted all the points from number 10. That was time, days, and height inches. And I still have this typed, right? The function is doing its darndest to make these 3 points fit on a parabola, which I guess apparently they do, right? However, this parabola is really flat. It's essentially a line. So we don't want to use this. We want a linear model because these points are significantly more linear than they are parabolic. So with that being said, the question asked, is it linear or quadratic? Number 9 was clearly quadratic the way the points were. Number 10 here, it's linear. So my equation that I'm going to write is y equals, this one's nice, negative 2x plus b, which is 36. So there's that equation. So if you look at these two sets of points, you can see in number 10 that it's going down 6 each time. You see that? 3 days went by, down 6. Another 3 days went by, down 6. Another 3 days went by, down 6. That's linear. That's slope. It's going down 6 over 3, down 6 over 3. That's slope. That is a line. Number 9, it gets, because of that quadraticness, the parabolicness, it starts to drop drastically. The first one only went down what? 8. But then the second one, you go over 2, all of a sudden, holy cow, we went down like 40. And then another one over, we went down like 70. So it gets quicker and quicker and quicker. That's that parabolic shape. Let me pause it again. Okay, and I'm back. So you can see these points. Oops, I'm not back. There you go. So you can see these points, and they're going up really quickly. Now, this could be a really, like, I guess, narrow, skinny, stretched parabola. But I can't help but notice that this looks a lot like our exponential parent function. Exponential parent function, right? This looks a lot like an exponential graph. It's starting to flatten out here at the bottom, but it's going straight up. And when I turn this on, so I've plotted all the points, and when I turn this on, it doesn't even want to fit. It can't even fit. And this r squared value is not 1. So it's trying its darndest to match these, but it can't. And so this one's neither linear nor quadratic. This one's exponential. It's taking off way too quick. Way too quick. So, in conclusion here with that one, so this one was quadratic. This one was linear. This one is neither. This one's the last question. We're obviously going to go back up to these, but this one's the last question of these with the word problems, which they haven't really been that wordy, right? But it's just getting used to the fact that data from the real world can become is quadratic, is parabolic. Like that, whether it's height, whether it's money, whether it's value, whether it's the path of something, we can represent it with a parabolic, with a quadratic function. The table shows a university's budget in millions of dollars over a 10-year period where x equals 0 represents the first year in the 10-year period. Use a graphing calculator to create a scatter plot. Which better represents the data, a line or a parabola? Use the regression feature to come up with a model, and then we're going to predict something. So let me pause for probably the last time here. All right, and we're back. Um, I can't help but notice that this is definitely not linear because it's wiggling, but it's definitely not a perfect quadratic. But I don't want to say neither either. Okay? I don't want to say neither either. I mean, yeah, we're gonna estimate it with a quadratic, right? It can't be real life isn't perfect, right? Not all the dots are gonna go on the line. It's just definitely not a line, and no other type of function stands out to me. You can see how it's like how it's trying to curve like up and down on the left as if this is like a line of symmetry, maybe potentially, right? So but we're gonna work with this, okay? I double checked all my points too. It was not like I did something wrong here with my points. So we're gonna work with this. So using a graphing calculator, which better represents it? A parabola. We don't want to say neither here. We want to say a parabola. So parabola. And explain? Well, it's definitely not linear. It's just like it couldn't possibly be a line because a line like if we drew a line through the middle of these points, right? It's totally missing like all of them. It's just, it's it's just definitely not linear. A line doesn't can't go down and then back up. It's just not possible. So, I don't know how you want to put that into words on your page. I don't want to write some essay here, but parabola is best, okay? I would at least say, the slope changes from positive to negative, right? And I'm putting that word slope in parentheses because there is no slope, okay? But like if you were to think of this as a line, the slope would be going down for these first 3 points and then turn around and go up for the rest of the points. A line can't do that. I just want to stress that. Okay, use the regression feature. Okay, that's already what's being calculated. I'll go ahead and write that down for you. Y equals 1.49 times x plus 0.17, interesting, plus 39.94. Okay. Use the model in part B to predict when the budget of the university is an insane. So, oh, these are in millions of dollars, by the way. So, this is 200, this is $22 million. This is 20, this is six, or not, sorry, 22, yeah, 22 million. Yeah, it's in millions. I don't know why I was struggling with that for a second. 22 million. Oh, you can't see what I'm clicking on. Sorry. This is, you know, 65 million, 92 million, 114 million, 128 million. So we want to know, when is it going to reach 500 million? So if this red line predicts the future of this school's budget, we essentially want to know, when does this red quadratic function reach $500 million? Don't try to sit here and like line it up, because you're gonna struggle, right? You're gonna be moving around this whole time. So how about we just plug it into our function? So let me go ahead and type the function that we just wrote out. Y equals, or I don't even need to write y equals. So 1.49, oh my gosh, 1.49 times x plus 0.17 squared plus 39.94. And we want to know, when is that going to equal $500,000, right? We want to know, when is this going to equal $500,000? Well, if we plot the line y equals, not 500,000, 500 million, 500 million, or, well, okay, the numbers are messing with me, right? So it's 500 million, but the number 500 represents 500 million. So where does our blue graph and our red graph come together? Voila. After 17.4 years. If you want to round that down to 17, if you want to round that up to 18, that's okay. But I'm going to write between 17 and 18 years. That's what I'm going to write. Between 17 and 18 years. All right. Beautiful. So hopefully you're feeling comfortable with how this data can become a quadratic shape, or how it could become linear, and that we need to identify between the two. That the C might have been the toughest question potentially, right? We just need to realize that this path represents the cost, and we're trying to figure out where it intersects. So that's why I plotted that 500. All right. I don't think we need to do every single one of these. The video is already a half hour long. I want you to be able to potentially finish your assignment here. Um, so before the video concludes, so you're watching this in class, we're doing 2.4 here. Um, I've shown you some things with Desmos, right? You're going to be cracking up Desmos, and you're going to be working on that assignment, and ideally you can walk out of the classroom with it finished. So I hope that that can be accomplished. You're going to see a lot of questions like these and a lot of questions like these. Okay, I mean, there's no surprises. So we looked at all of these. Let's like maybe do one of each. Let's do, one graph, one of these, another graph, and one of these. Okay. So four more, but we'll do them really quick with Desmos. We'll do them super quick with Desmos. So just like the lines, like, you just plug some points into the table and it starts predicting it for you. Plug some points into the table and it starts predicting it for you. It's truly that simple. Okay? Plug some points into your table and it starts predicting it for you. So when I plug in, pausing. So when I plug in my 2 points, 0, 3, and 2, 1, and it starts predicting my parabola for me. Oh, interesting, right? So we're living and learning here. So Desmos thinks this is the vertex, 2, 1. But if you look at our picture, 2, 1 is not the vertex. So how can we, this is a learning moment for us. How can we convince it that that is the vertex? That 0, 3 is the vertex. Well, parabolas are symmetrical, right? So it's confused. It's just been given 2 points, and it's like, which one do you want? Which one do you like, right? Well, if we flip this around, well, not if we reflect it, if 2, 1 exists, well, then guess what? Negative 2, 1 exists on the other side. Clutching. Negative 2, 1. And now it's like, oh, here's the symmetry. That one's got to be the vertex. And with that, boom, it's given us our equation. So you might have to add in your own additional point to convince it that this one is the vertex instead. Again, if I get rid of this point, oh, well, now it's convinced. That's interesting. Now it's not confused anymore, but I had to type this first. That's fascinating. Okay. So here's our A, H, and K for number 2. Y equals negative a half, parenthesis, x minus 0. Sure. Squared plus K, which is 3. Big ideas, I would assume, is going to ask you to write it as a fraction, so I wrote negative a half there. All right. All right, number 4. Passes through negative 4, 7, and has a vertex at negative 2, 5. Again, you just punch them right in, and it's going to calculate it for you. I mean, spoiler alert, spoiler alert, right? If this is the vertex, we know that this is x plus 2, and we know that this is plus 5. You should know that. We should all know that right now. Left 2, up 5. Left 2, up 5. But the thing is if it passes through the point negative 4, 7, does it open downwards? Does it open upwards? Was there a stretch? Was there a shrink? That's the ambiguous part. That's the part that we're not 100% certain. It could just be this, right? It could just be that, and we're done. But if it was stretched or shrink, then we need to be aware of that. So let's go ahead and punch these points in. So negative 2, 5, and then negative 4, 7. And then let's get rid of this because it's mighty confused. So we really want negative 2, 5 to be the vertex, and it's clearly not. So again, using our knowledge about symmetry here, we need to introduce a third point. If this is the vertex at negative 2, 5, there should be the exact same point on the other side. So if this is negative 4, 7, and this point's in the middle, there should be one at 0, comma 7. Does that make sense? I know you can't raise your hand and ask a question right now, but I'm creating that symmetry by introducing this third point. I'm like, well, if this point's here, then this point has to be here as well. I'm creating that symmetry. And now Desmos is convinced that, oh, that's the vertex. Gotcha, right? Now we've convinced it. So you can see here that H and K are exactly what we wanted them to be. And A is a half. Now, I can see some of us getting confused by that H and being tempted to want to write x minus 2. But you'll recall, it's always the opposite, right? I wrote plus 2. But the vertex is at negative 2. Indeed it is. But when you subtract that negative number, it becomes positive. You got to remember what the equation is that we typed. Minus h. So when you subtract negative 2, it's going to become plus 2. Okay? 2 more and we're done. Number 6. They've given us 3 points in number 6. Let me go ahead and type those real quick. Negative 4, 0. Negative 3.5, negative 1/4. And then negative 3, 0. So these are our x-intercepts because it's crossing the x-axis. This is our vertex, okay? And I want to type something different here because number this problem, I should have read the directions before starting. It says to write the equation in intercept form, which is x minus p, x minus q, okay? So if the x-intercept is at negative 4 and an x-intercept is at negative 3, we know this to be true. The fact that we could assume the vertex, that's the easy part for vertex form. We can assume that this is plus 4 and this is plus 3 because our intercepts are at negative 3 and negative 4. But let me go and show you how I would type this in. Same idea with the y1, right? A times x minus p, x minus q. And this needs to be x1, x1. Look at that. Boom. So the purple graph and the red graph are the same, in case you can't tell. This one's in vertex form. The purple one is in intercept form. And you can see how our intercepts are lovely at negative 3 and negative 4. Boom, boom. And A is 1, apparently, in this case. A is 1. So there is no stretch or shrink. So we're done. Crazy, right? There is no stretch or shrink on this problem. A is 1. So when I write that out, boom, we're done. A is 1. We don't have to write it. I mean, you can write 1, but not required at all, right? Last one. Last one. The x-intercepts are at 7 and 10. Now, it didn't give us the points, but we need to realize that the x-intercept means 7, 0, and that the other x-intercept means 10, 0. Okay? We need to realize that. So that way we can plug that point into our table. So I'm going to change this to 7, 0, and change this one to 10, 0. And it passes through. Not that that's the vertex. It doesn't say that that's the vertex. It just says that it simply passes through the point negative 2, 27. Okay? So be careful about assuming that that is the vertex because it does not say that. So you can see here that these are the x-intercepts and that this point is randomly up here. So the vertex is not negative 227. The vertex is whatever's down here, all right? But this is accurate. We've got our two x-intercepts and our random point. We can see all the numbers lining up here, and we can go ahead and write that equation. That's 0.25, in case you didn't realize, is a fourth. So A is 1/4 times x minus 7, x minus 10. It does not matter whether you write minus 7 minus 10 or minus 10 minus 7. Okay? It does not matter which way you were to write that. And there is our function. So to put a bow on this as we hit the 40-minute mark, to put a bow on this, don't be, so don't be alarmed by how the problem is given to you, right? A graph, a sentence, a table. Just realize that the points, whether they're in a sentence, whether they're on a graph, whether they're in a table, need to go into the table on Desmos, and you type out the right function. So the two versions that I was typing, if you need to write them down, you like just haven't ever written them down this whole time, which is fine, right? You were just like, well, he's already typed it. I'll just let him do it. Here they are, all right? This is vertex form, and this is intercept form. It's just that I'm changing the y and the x to y1 and x1. And I'm using the little squiggly, the approximate. But this is just vertex form, and this is just intercept form, and it approximates it. Okay? So, again, with the remaining time, you might have already done the daily quiz. You might not. I don't really know what the order of events is here today. But if you haven't done the daily quiz, you're gonna do the daily quiz, and you can start on the big ideas assignment, big ideas 2.4. So with that, I will see you next class period, so that way we can review. I hope you enjoy the rest of your day. If I don't see you for whatever reason, right, enjoy your long weekend. I think I should see you, but if for some reason I don't, enjoy your long weekend. Um, I'll catch you later. Thanks for paying attention. Thanks for learning. Bye-bye.